and we'll move on to the next module where we'll talk about gradient descent. How many of you have done gradient descent before? Almost all of you. Okay. So what we want to do is find a more efficient and principled way of navigating the error surface. Is everyone with me in that? Okay. And the goal is to find a better way of doing this. Okay. Fine. So let's start by setting up things. We'll define some notations and some parameters and so on. And from there on, we'll try to come to the algorithm. Okay. So my parameters in this case were w comma b. What I'm going to do is I'm going to put them into an array or a vector, right, and call that vector as theta. So theta is the vector of parameters, and theta belongs to R what? R2, right? There are two parameters here, so it's a two-dimensional vector. Okay. Now what I want is, again what I'll do is I don't know what the value of w comma b is, so I started with a random guess. So that's always going to be my starting point, right? I'll always start with a random guess, and from there on move on to good values. Now once I've started with a random guess, I want you to tell me some changes that I can make to w and b so that I land up in better situations, right? That means I land up in situations where the error is less. Is that fine? Okay. So that change in w and b, I'm going to call it as delta w and delta b, and that again is a vector which is storing these two values. Okay. So this is the picture, right? I want to take theta and I want to add a small change to it. So this is my theta. This vector is actually theta, right? This is the theta vector. I want to add a small change to it, which is again a vector, right? This is delta w comma delta b, such that I'll get a new value for theta nu, right? So theta nu would be what? Actually, theta nu is equal to w nu comma b nu, right? Is that fine? That's what theta nu means. Okay. Now what has happened is actually when I've added delta theta to theta, I've moved in the direction of delta theta, right? I've come from here to here. Okay. Now I'm going to be a bit conservative, and I'm going to say that while I'm okay in moving in the direction of delta theta, I don't want to make a giant stride. What I'll do is I'll just move by a small quantity in that direction, right? So this delta theta is this large magnitude. So all I'm saying is that I'll move in that direction. I'm fine with that. Okay. But I don't want to make a giant stride. I'll just take a small stride in that direction, right? So eta is a scalar which actually scales down delta theta. Okay. So now if I'm going to take only a small step in that direction, instead of this large change, I'll just get a smaller change, theta nu, right? So the red vector is actually going to be the movement which I make. That's the new value of theta. So theta nu is equal to the original theta plus a small step in the direction of delta theta. So everything is clear? You're done? We're done with gradient descent? What is missing? What is delta theta? Right? I'm telling you I want to move in a certain direction, but what is the right delta theta to use? How many of you know the answer to this? What is the answer? Move in the direction opposite to the gradient. Why? Where does that answer come from? Not the ML class folks. How many of you know why we need to move in the direction opposite to the gradient? Why? Okay, we'll see. Okay, so that's the question that we need to answer. If I give you an answer to this question, then what is it I'm doing? I'm giving you a principled way such that you start from a random value of theta, move in certain direction, and it will ensure that your loss has decreased, and then you have to keep doing this, right? So that's the setup, and the answer to this comes from Taylor series. So now what I'm going to do is, I'm going to give you the right direction, delta theta, fine? And for ease of notation, I'm going to call it as u. So remember what this delta theta is? What is it? Change in w, comma change in b. So it's a vector in R2. Remember that? Okay. I'm just going to call it as u. Now this is what Taylor series tells me. What it tells me is that if I'm at a certain value of theta, and if I want to change that value a bit, then what is going to be the new value of the loss function, or any function for that matter? And this is the formula for that. Okay. Now let's see what are some quantities here. What is this quantity? Scalar, vector, matrix? Scalar. This Vector. We just did that, right? It's a vector. What about this? What is this quantity actually? Gradient. What is a gradient? What is a gradient? No, you're telling me how to use the gradient. I'm asking you what is the gradient. You're giving me absolutely correct and absolutely useless definitions. That's a very good answer. Okay. So now what I'm going to do is I'm going to digress a bit. Okay. And I'm going to tell you something about derivatives, partial derivatives and gradients, and then we'll come back to this. Okay. So now suppose you have a function L. This is L in my handwriting. This is a function of W. Okay. And say this function is W square. Okay. Now what is this called? The derivative of the function with respect to W. This is the derivative, and you know this is 2W. Okay. Now suppose I have a function B square. Now what is this quantity? This is the partial derivative of the function with respect to W. Why partial? Because it's considering B as a constant and taking the derivative with respect to only one of the variables, right? This happens to be. And what is this quantity? Oh, sorry. So it's W comma B, right? This is the partial derivative with respect to B. Okay. Now can you tell me what is a gradient? So the gradient is nothing but just these two partial derivatives taken together and put into a vector, right? Now suppose I had a function which depended on 100 variables. What would the gradient be? Size of the gradient? R100, right? It would be a 100-dimensional case. Okay. So now can you tell me with this, I wouldn't say knowledge, but this primer, can you tell me what this is? This is a gradient vector which is right there in front of you in red ink. This is what it is, right? Fine? Everyone okay with that? So actually the right way to write this, and probably we need to correct in the slides, would be theta. So remember that theta is equal to W comma B. So this is the derivative of L theta with respect to theta, which is nothing but the collection of the partial derivatives with respect to the components of theta. Is that fine? So everybody understands what's a derivative, partial derivative and gradient? Okay, fine. So now the gradient is a vector in this case. Fine. Okay. So now what is this quantity? It's a, no, it's, what is this? The dot product between these two vectors. Okay, fine. Now one last thing, and many more things actually. So what is this? Square of the gradient. This is not the square of the gradient. What is this? Hessian, fine. Everyone knows the textbook. What's it? Can you tell me what does it? It's a scalar, vector, matrix. Matrix. What's the size of this matrix? 2 by 2. What are the elements of this matrix? Second order partial derivatives, right? So it's the gradient of the gradient, right? Is that fine? So what does that mean? You had this gradient. This is the gradient. Now you want to take the gradient of this again with respect to W comma B, right? That's what this means. It's a gradient of the gradient, right? So what that means is, you'll take the gradient of the first quantity again with respect to W, so that would be dou square by dou W. What would this quantity be? Okay, what would this be? and you can fill in this quantity, right? So now it's clear what the Hessian is the derivative of the derivative, and it would be a matrix. Okay, is that clear to everyone? Yeah. So I have a habit of doing a lot of these basic stuff. I know that the top 20% of the class gets really pissed off when I do this, but as a philosophy, I teach for the bottom 30% of the class, so I don't mind that. And the other thing is I use slides, so I don't write a lot of math, so I can cover a lot of material despite doing all this basic stuff, right? So I'm going to stick to that. What I'm trying to say is that write this in the feedback that you don't like this basic stuff, but it's just that I'm going to ignore that feedback, okay? I mean, just being honest, right? So I like doing this because it just takes me 10 minutes to do this, and for the rest of the class, I don't have to look at blank faces afterwards, right? So it really helps me a lot, okay? Fine, so is that all clear? All the quantities here are clear. So now, so this is the gradient, this is the Hessian, and now eta, remember what did we say about eta? It's a small quantity. And what do we do with small quantities always in maths? We ignore them, right? So once we take their powers, we always ignore them. Whether it's correct or not, who cares? I mean, someone has told it it's good to ignore, so we'll ignore it, right? So now all these higher order terms we can ignore, right? That means I'll only consider this. Fine? So let's again look at what the setup is. The setup is that I have some value of theta. I want to move away from that value such that, what do you say about this loss compared to this loss? I'll call this the new loss, and I'll call this the old loss. What is the relation between them? The new loss should be less than. So if I or someone gives you a u, okay, someone gives you this u, okay, then when would you say it's a good u? If this condition holds. Everyone agrees with that? Right? So I've found a good direction to move in if this condition holds. Now, this condition actually implies that this condition should hold. Right? This is L theta plus eta u, right? So if I just do minus here, I get this, right? So this quantity, which should be less than equal to 0, implies that this quantity should be less than equal to 0. And remember, eta is a positive constant. Okay? Why can't it be negative? Yeah, why? Because we wanted to take a small step in that direction. If we make it negative, we will do what? We will reverse the direction. We don't want that as of now, right? So eta is, that's for a positive quantity. So that means this quantity should be less than 0. Is it fine with everyone? Okay. Okay. So far, after all this story, what we are left with is this condition should hold for the u that I am trying to choose, so that I can be sure that I have chosen the correct u. Right? And the definition of correct u is that the loss at the previous step, the loss at the new step should be less than the loss at the previous step. Is that fine? Okay, so that's what we have arrived at. Now, what is the range of this quantity? That's why I asked you, what is this? This is a dot product. Okay, I'll leave it at that. So now you tell me what's the range of this. People from the ML class cannot answer. Did I cover this in the ML class? No? Okay, fine. What is the range of this? Not a very hard question. Plus or minus? Very good. How many of you understood that answer? He said plus or minus mod of u into mod of gradient, the gradient vector, right? Why is it so? Easy. Let beta be the angle between ut and this, sorry, it should not be u transpose, between u and the gradient. Then we know that this condition holds. Cos beta is given by this quantity, and we know that cos beta lies between -1 and 1. Okay. Now, if I just say that this quantity is equal to k, then I can just get this condition. Okay. Now, let's see what are we trying to do. We are trying to find a u such that this quantity is negative. Okay, okay. We're trying to find a u such that this quantity is negative. Now, if I just stop at negative, we would like to make it as negative as possible, right? Because the more the negative it is, the more will be the decrease in my loss function, right? Because this quantity tells me how much my loss decreases. So the more the negative it is, the more the loss will decrease. So let me make it as negative as possible. Now, what is that value? When will that happen? When alpha is, you know the answer, you started with the answer. No. What is that one phrase which you have marked up? Move in the direction. Okay, now think of that. What would happen when this is the most negative it can be? What would the angle be? 180 degrees. How many of you get that? Because when this is the most negative, that means the cos beta is actually -1. And when is cos beta -1? When the angle is 180 degrees. That means u should be such that it is at 180 degrees to the gradient. Hence, repeat the phrase. Move in the direction opposite to the gradient. Is that fine? Everyone gets it now? Why you need to move in the direction opposite to the gradient? Okay, fine. So this is what the gradient descent rule is. You are at a particular value of theta. You want to move to a new value of theta such that your new loss is less than the current loss. What gradient descent tells you is move in a direction opposite to the gradient. Okay. So are you fine with this? Now with gradients I've come to scalars, but I'll just explain what I've written here. So this quantity is nothing but theta t plus 1, right, is equal to theta t, right, and what is this? Right. So the new theta is equal to the current theta minus, why? Because we want to move in the direction opposite. So it's basically theta t plus 1 is equal to theta t plus eta into a negative direction, right? The direction negative to the gradient, hence you get that minus out. Okay. So is that clear? Now what are these quantities? Let me just take that carefully. So this quantity is gradient of the loss function with respect to w, sorry, the partial derivative of the loss function with respect to w evaluated at w is equal to wt and b equal to bt. What does that mean? So remember, when you are dealing with derivatives, there is always a formula and then a value at a particular value. So what's the derivative of x square? With respect to what doesn't matter, 2x. Okay. Okay, so the derivative of x square with respect to x is 2x. What is the value of this derivative at x equal to 1? 2, right? So you see the difference, you have a formula which is 2x, now you substitute a particular value and you get the value at that particular value, okay? So that's what this means, because you are already at wt comma bt. Now you can't subtract a formula from here, right? You have to subtract a value. So you know what the formula is, you plug in the values of wt comma bt, get that value and subtract it from your current wt. Is that fine? Okay. So everyone completely understands what the gradient descent rule is. Okay. Fine. Good. So now we have a more principled way of moving in the WB plane. What do I mean by that? Remember, this was our WB plane. This was our error. This is something what our error surface looked like. It was this flying carpet. I was randomly moving on the WB plane earlier, right, and trying to guess what the error is, or trying to compute the error and then settle for a particular value. Now I have a more principled way of moving in the WB plane. I know what is the next step based on the current step. I just need to move in the direction opposite to the gradient. Okay. So let's try to, so this is what it tells me for one step, but I need to keep doing this till, what's that golden word? Convergence, right? I have to keep doing this till convergence. Okay. So let's create an algorithm out of this rule. I'll start at time step 0. I'll do this for some max iterations, right? Instead of saying till convergence, I'll do it for some iterations. At every iteration, this is how I'll update my weights. I'll take the current weights, subtract the gradient from that, and get the new state. Not subtract the gradient, subtract this quantity and get the new weights. So now is everything clear? Is the gradient descent algorithm done? Can you do it for the toy network which I had? Is there something still missing? Eta is fine, we'll take a small value, 0.01 or something. I've still not told you what these are, right? I mean, it's okay to write it. You know these are derivatives, but what is this actually? Right? So let's see that now. So that's what we are going to see next, okay? Oh, I'm really going slow today. Fine. Do you guys need a break? You're really in a hurry to wind up the lecture and go. Are you sure you don't need a break? Okay. I don't know whether to be happy about it or sad about it. I'll be happy. Okay. I'll assume that you're enjoying the lecture so much that you don't want a break. Okay. So now we want to find out, our quest is for this the partial derivative with respect to W and partial derivative with respect to B. That's the thing which we had plugged in the formula, but we don't know what that is, right? So we need to find that out. So now for simplicity, let's assume there is only one point to fit, which is x comma y, right? So earlier we had this x1, y1 and x2, y2. Now I'm just assuming there is only one point, which is x comma y. So now what is the loss function? Earlier I had this summation over I equal to 1 to 2, but I have just one x comma y, so I'll just use that. Okay, this is what my loss function. And what are the quantities that I'm interested in finding? One is this, the partial derivative of this loss function with respect to W. Okay, so let's do this. Let's actually derive this. So this is what it looks like. Now you have to help me in deriving this. What will I do first? Tell me the next step. 2 into f of x minus y and push the gradient inside. Push the derivative inside. Is that fine? Anyone who has a problem with this? Okay, next. Y is a constant. This is the true y, remember. So that's why this is a constant. This is not the predicted y. Okay. Now this quantity. What is f of x actually? Sigmoid function, right? So I'll just write it. Now this is the quantity that I need the derivative for. So I'll just write it here. What's the next step? This is of the form 1 over x. So what will it be? Minus 1 over x square, and then you put the derivative inside. Is that fine? Now the quantity inside is of the form e raised to x. So the derivative is e raised to x, and you push it inside. Is this fine? So this on slide should come, both these are coming together. So is that fine? Okay. Now what is this actually? F of x. What is this? This is actually 1 minus f of x. Just take my word for it for now. You can go home and work it out, right? So this actually, if you do 1 minus this and do some trickery, you will get to this quantity, right? So what you get is a very simple formula, f of x into 1 minus f of x into x. So I'm going to substitute back here. So now I exactly know what the partial derivative of w is. Okay, fine. So if there is only one point, then this is what the partial derivative with respect to w is going to be of the loss function, right? If there were 2 points, what would happen? If there were 2 points, my loss function was, this is a sum of 2 elements, and I am taking some derivative of a sum. I'll get a sum of derivatives, right? So how many of you will not cringe if I say this is the answer? Anyone who has a problem with this? You get this? How many of you don't get this? How many of you get this? Okay, good. Fine. Now can you do a similar thing for B? Can you tell me the answer without actually deriving it? Yeah, I can perfectly understand what you're saying. This x won't be there, right? Because this last x that you see here came because w into x was there. But with B we are not multiplying x, so what you will get is this. You can go home and check. Okay? So now we have everything that we need. Now we actually have everything that we need. Okay? No more trick questions. So now we'll write code to do this. Okay, we'll actually implement the code and see what happens. So these are the two data points that I had, 0.5, 0.2 and 2.5, 0.9. The first thing which I need is something which can implement the sigmoid function. So this is 1 over 1 plus e raised to minus wx plus b. Is that fine? Okay. Now I need something which can compute the error. So this is summation of half into f of x minus y the whole square. I go over all the data points, summation of half into f of x minus y the whole square. Is that fine? Now what I'll do is, I'll take this, try out a lot of values of w comma b and plot the error surface. Okay, but this is only for illustration. In practice I'll not do this. We just know that this error surface exists. I just want to verify that whatever algorithm I come up with does an efficient navigation of this error surface. That's what I want to verify. Okay, that's why I'm plotting this. Okay, next I need a function which can compute grad of b. We just saw this on the previous slide. This is f of x minus y into f of x into 1 minus f of x. Right? Simple? Everyone is fine with this? Then I need a function which can compute the grad with respect to w. Same thing, except that I have this x at the end. So I have all the ingredients in place. Now what will I do? What is the next thing that I'll write? The main loop. Right? I'll write the main loop now. Okay? So this is what the main loop looks like. I start with some random initialize for w comma b. Remember that our initial theta, which is composed of w comma b, is going to be some random guess. So I started with a random guess, which is minus 2 comma 2. I've chosen eta to be 1. That means I'm not going to be conservative. I'm going to move in the direction of the gradient. Okay? If I'd chosen at 0.01 or 0.001, I would have been conservative. And I'm going to run this till 1000 epochs, which is my notion of convergence. Okay? Now in each epoch, what I'm doing is, for every data point, so remember that this gradient with respect to w was a summation of I equal to 1 to 2 and that formula, right? So for each data point, I'm computing the grad, adding it, right? So that's the summation part. Similar thing I'm doing for b. Once I have computed the gradient, which is the summation quantity, I'm just moving in the direction of the gradient. Is that fine? Everyone understands the code? It's simple Python code and it does exactly what I had shown in the pseudocode. Okay? Now let's execute this code and see what happens. Okay? So I'll start with my random point, which was minus 2 comma 2, and now I'm going to actually run this code and keep plotting what happens on the figure. Okay? So just pay attention. Fine? So now here's how the code is running. See what is happening? What is happening actually? So at every point, I'm changing my w so that I'm moving in the direction of the gradient. I keep doing that. As I keep doing that, my error keeps decreasing. Why? Because that's exactly what we got from Taylor series, right? If we do this, the error is bound to decrease, right? And then we keep doing this, and after a few iterations, we'll actually reach almost the valley, which is the 0 error, right? And this same thing would happen if you start from anywhere else. It will keep moving in a principled way and reach the low error configuration, right? Now some of you would say that maybe this was the shortest path, right? It could have just rolled over from there. But that is not a principled way of doing that, right? The principled way of doing it is to move in the direction of the gradient. You might take a longer route, but reach your destination. Taking shortcuts is always risky in life as well as here, right? So don't, please, this is an advice for your assignments and so on, right? So yeah, so this is the more principled way and we'll reach the solution, right? So that's what is happening here. So we actually derived everything that we needed, and this is all you need to write for gradient descent for this toy example that you had. Now answer this question. Now suppose I had 100 such variables. Instead of w comma b, I had 100 such variables. What would happen? We don't try to visualize it in terms of the code. I'll just need to have these functions for all of those, right? I'll have to calculate it by hand, but still doable. It's just a lot of tedious work. Of course, later on we'll see a more refined way of doing this, where we can do a lot of these computations at one go, right? So we can directly start operating in vectors as opposed to scalars here, right? I'm treating W and B separately here. I could have actually had a function which tells me grad of theta directly, right? And later on we'll see something like this. Okay, but for now, the code is still running here. Now it suffices. So later on we'll see gradient descent in more detail in the course, and we'll also see a lot of variants of gradient descent. But for now it suffices that we have an algorithm which can learn the parameters of a sigmoid neuron, right? So just as we had the perceptron learning algorithm, we have the gradient descent learning algorithm which can help us learn the parameters of the sigmoid neuron starting from random values, and it gives a principled approach for doing that.